Today we're going to do a lab where we're going to try to find the coefficient of static friction between two surfaces. Now notice on this slideshow up here, I have two blanks, between blank and blank. You're going to pick the two materials. One of the materials is almost certainly, for you, going to be a wooden block. One of these wooden blocks up here. But the second material can be, it could be the floor, it could be the top of a desk, it could be the top of a table, it could be whatever. You pick a second surface, doesn't matter what it is. Just make sure you specify which two materials you're using. Of course, there's going to be three variables, as always, three sets of variables as always. One manipulated variable that's going to become pretty clear to you soon. One responding variable that should become pretty clear to you soon. And then we've got, 1,000 control variables. How many do we ask you to list? We don't have a number for that, right? 1, 2, 3, whatever the really important control variables are. If you list the temperature as a control variable, that's fine, but I don't really care about that. Okay, what's really important to keep the same in this lab, that's what I really want to see for your control variables. Now, your materials, you're going to list for me in words. You can insert pictures if you want, but you certainly have to list them in words as well. Our materials are going to consist of a triple beam balance scale. The triple beam balance scale is going to be used to find the mass of the wooden block. The wooden block that's right here that you're pulling along, well, either the floor or the table or the desktop or whatever. You're also going to have, in addition to the wooden block, some masses, some steel masses. So you're going to have a mass set that you're going to use to make the wooden block heavier over each consecutive trial. Now, attached to that wooden block is going to be a string. You don't have to list that as a separate thing because it's already attached to the wooden block. You can just consider it to be part of the wooden block. You're going to hook onto that string a force sensor. Now, you've done a couple of labs where you've used a motion sensor. This is going to be the first time when you use a force sensor. That force sensor is going to be connected by a cord to your air link. This is actually an older version of the air link that you see right here. That's not a big deal. Okay, you know what the current version looks like because you've used it before. And that air link is going to be connected via Bluetooth to your phone. Then, of course, your phone, you're going to see your data and you're going to end up recording that. Good news is for this, you don't have to export data again. All you have to do is read it right off of the graph that you see on your phone and just write it down on a piece of paper, on this piece of paper right here, and then copy it over into Google Sheets and do the graph that you're going to end up needing to plot there. Does that make sense? So what's your procedure going to look like? Well, set up your apparatus as you saw it set up in the photo that you just saw there. The force sensor is going to have a little button on it, a little 0 button on it. Before each trial, make sure you press the 0 button right there. Okay, sometimes if you don't press the 0 button, it's fine. But sometimes if you don't press the 0 button and you're not applying any force, the scale will read 0.2 newtons or negative 0.1 newtons. Well, that's clearly wrong. If you're not pulling on it, then the force should be 0. So press the 0 button to make sure that it's reading 0 when you're not pulling on it or pushing on it. And do that before each trial. Measure the mass of the wooden block. Now, I say here including the mass of any masses on the wooden block. What I'm going to say you should do here is measure the mass of the wooden block, and then just, because we only have 3 triple beam balance scales and we have to share them, just add the mass, like mathematically add the mass to it. Does that make sense? Like if you have a wooden block that's 200 grams and you add a 30-gram mass to it and a 60-gram mass to it, then you would say, without remeasuring, you would say that it has a mass of 290 grams. Okay? So measure the mass of the wooden block once. Make sure you include the mass of any steel masses that you put on it, but you don't have to remeasure it. You can just add them mathematically. It says hook the force sensor. It should say hook the force sensor onto the string connected to the wooden block. Press Start on the SparkView app. And by the way, when you're in the SparkView app, you're connected via Bluetooth, you're in the SparkView app, you're going to see a few options for the sensor. What you're going to want to pick is force pull. Okay, it says, one says force push, one says force pull. That's going to ensure that you get a positive value for force as you're pulling. If you don't click that one, then whenever you pull it, it's going to show on the graph a negative value for force. It's not a big deal because you could just drop the negative. Okay, but it's a little bit easier to see if you get a positive value. Okay, force, I think it's actually force positive pull. You'll recognize it when you see it anyways. So you click on that one. You're going to see that graph of force versus time. Force versus time. And then I want you to press Start on the SparkView app. Then pull the force sensor. It's important to pull it parallel to the ground. I've italicized that because of the importance of that. If you pull it up like this at an angle, pull it up like this, then we got a problem. We're going to assume later on in this lab that the normal force is equal to gravity. But if I'm pulling up on it at an angle, the normal force will not be equal to gravity because I'm helping the normal force along there, the force of the floor pushing up. So I want you to make sure that you pull it parallel to the ground, just gently, pull it a little bit harder, a little bit harder, a little bit harder until the block begins to move. And then you've done that trial. Press Stop on the force sensor, record your data. You should see approximately a graph that looks like this as you perform that trial. The force increases, and then it should decrease, and then it should be flat like this. What does that value right there correspond to? Yep. That's going to be the maximum force of static friction. That's the force that I have to pull with to get it moving, right? FSF max. Now, what do you think this horizontal flat line represents? Anyone? Yeah, Jen? That's the force of kinetic friction, because you know that the maximum force of static friction is bigger than the force of kinetic friction, right? I pull it, I pull it, I pull it, I pull it, and finally it moves. And then what happens? The force of kinetic friction kicks in, and it's going to be a little bit lower and a constant value. This is the value that you want to read right here. Okay, this is the value that you want to read right here. If you want to read it right off the graph and just record the value, that's fine. But if you go to the bottom right-hand corner of the app, there's a little arrow that you can click to get you to a data table. And if you want to go to the data table, you can actually scroll up and down the table to find the exact maximum value of force. Does that make sense? So read it off the graph, read it off the table. I don't really care. But the bottom line is you don't have to export your data here. You're getting it off your phone, and then you're done. So that's trial one. Okay, I've got my mass, and I've got my maximum force of static friction. Then I'm going to do it again. I'm going to repeat it. I'm going to repeat, I said steps 2 to 4 10 times. I'm going to repeat steps 1 to 4 10 times because I want to press the 0 button each time. Each with a different mass of the wooden block. Now, little hint here, you should start off with not just the wooden block. The more mass you have, the better. So don't just use the wooden block. Like, put a bunch of mass on the wooden block. Okay, and then when you go to your next trial, put more mass on the wooden block. Don't go up by 20 grams each time. You're not going to notice a difference between trials. Okay, go up by as much as you can. We got lots of masses up here. These rectangular boxes have the wooden blocks in them. These bigger boxes right here have bigger masses in them. And you can pilfer from all of these bigger rectangular boxes to grab different masses to add mass to them. You can share between groups, do whatever you got to do. But don't just add one of these piddly little 50-gram masses. Okay, that's not going to make much of a difference. Add something significant, like add a 50 and a 100 so that it goes up by 150. And start with something that's fairly big as well. Yep? Sorry? You could. Yeah, you could do 2 wooden blocks. The downside of that is that you're going to have to physically measure the mass of the second wooden block, whereas if you put just these masses on it, it's printed on the side of them. So everybody has to measure the mass of 1 wooden block, right? If you use another one on top of that, then you're going to have to measure the mass of the second one as well, because it's not printed on it. Okay, but really, whatever mass you want to use. If you want to use, a set of keys or whatever, as long as you measure the mass, it's fine. Then of course, once we have data, we do what we always do. We plot a graph. And this particular graph is going to be the maximum force of static friction versus the normal force. This is what my data table is going to look like. Mass in kilograms times 10. And maximum force of static friction in newtons times 10. And remember, again, that maximum force of static friction comes from this number right here. Now, you guys know enough. We've done enough things before in Science 10 and Physics 20 that your graph isn't going to look as perfect as I'm drawing it here, right? But if you use a big enough mass, it's going to be pretty good. You should recognize the shape. It's not going to be perfect, but you should recognize the shape so that you know where to pick your maximum force from. If it doesn't look at all like this, something's up and you should probably do another trial. Okay, don't just find a maximum force from any shape. It should look pretty much like this. Now, if you're late in turning off the sensor, well, then you might get something, like over here that's crazy, right? Or if you start it too early, then you might get something over here, right? But the bottom line, in the middle, you should get something that looks pretty much like this. Pick your maximum force from that, and then, of course, record your mass. We've already got these two columns in our analysis table, mass and maximum force. Now we've got to find the normal force. How are you going to get that? Yep.
Gravity times the mass.
Yeah, it's just the mass times gravity. Make sure your mass is in kilograms, though. If you happen to record it in grams, that's okay if you record it in grams, but make sure that you specify that it's in grams and then convert it to kilograms to find the normal force. My suggestion would be just convert it to kilograms right away, and then you don't have to worry about it later on. I think on the paper that I gave you, there's only space for 8 trials, I think, but there really should be 10 trials there because you had 10 pieces of data. Then you plot your graph. Maximum force of static friction versus normal force. And you're going to determine from that graph the coefficient of friction. Here's what the graph looks like. FSF max versus FN. Although when you plot your graph, you're going to write it in words, not in symbols like this, right? You should get more or less a straight line. Looked at the groups this morning, and they were good. They turned out really good. Have Google Sheets plot that linear trend line for you. It should be linear. Because it's linear, straight line graph, you get an equation in the form of y equals mx plus b. Display that equation. Y is equal to 0.64x plus, well, it should be 0, but might not be exactly 0. The y-intercept, right, should go through the origin. But if it's not exactly 0, that's okay. Now I'm going to show you an analysis to find the meaning of the slope here, how that relates to the coefficient of friction that we're really trying to find from this lab here. This is an analysis that you're going to use a few times through Physics 20, but you're going to use a lot through Physics 30. In fact, in January of next year or June of next year, you're going to get a question on your diploma exam in Physics 30 where you have to analyze a graph that you've never seen before, using the technique that I'm going to show you here today for the first time. This is a straight line graph. A straight line graph, any straight line graph can be represented by what equation? We all know this. Y equals mx plus b. Good. So write that down. The equation that represents the graph, y equals mx plus b. Now what I want to do is replace the y-axis with whatever appears on the y-axis. Y is FSF max. What does m stand for there? What does m stand for? No. Not mass. Y equals mx plus b. M stands for the slope of the graph. Now I'm going to actually write in the word slope here because I don't want anybody to get it mixed up with mu or mass. Right? Change it to the word slope. X, what's on my x-axis? My normal force. And you should find that the y-intercept, b, is so small that we can effectively make it 0. So just cross it off. So there's the equation that represents this graph. Now what I want you to do is get an equation from your data sheet that has FSF max and Fn in it. It's going to be this one. So blue one comes from my graph, black one comes from my data sheet. Now I want to cross off this because it appears in both, the one that came from my graph and my data sheet. And I want to cross off this because it appears in both, the one that came from my graph and the one that came from my data sheet. What am I left with in my graph equation? Slope. What am I left with in my equation sheet equation? Mu. So the slope would therefore be equal to the coefficient of friction. And that's what you're trying to find, right? So Google Sheets is going to give you the slope of the graph. You just need to recognize that the slope of the graph is the coefficient of friction. Do you see what I just did there? Now, if you couldn't do that on your own, we talked about that a little bit yesterday, right, with a problem that we did. If you couldn't do that on your own at this point, that's okay. If you can't do that on your own by the end of Physics 30, then we have a problem. Okay, but we're seeing it for the first or second time. It's not the end of the world if you're having a little bit of trouble with that, as long as you kind of follow along with me. Now, I would like you, when you hand in your lab, to show me this analysis. Okay, even though in the end it says we know that slope is equal to mu, and you calculate the slope and you got your answer, show me that analysis. There's value in copying that out. Okay, you copying that out is going to help you a little bit to internalize how to go through that process for down the road when it really matters to us. You know what comes next, right? This is analysis because we've done something with our data. What comes next, of course, is our conclusion, which is the value of the coefficient of friction is. This is known. How do we know it? What you're going to do here is just briefly describe what we did in our analysis. This is known because the slope of a force versus force graph is this value or whatever. 2 or 3 good sources of error. And of course, the suggestions for improvement.